Download this code from codegive.com, link in the description below. OK, let's dive into the world of concurrent hash maps in Java, focusing on what you need to know for an Infosys interview, and beyond. This guide will cover the concepts, implementation, usage, advantages, disadvantages, and common interview questions. Introduction to concurrent hash map. The need for concurrent hash map. In multi-threaded environments, traditional hash map isn't thread safe. Multiple threads accessing and modifying a hash map simultaneously can lead to data corruption, lost updates, and unpredictable behavior. While hashtable provides thread safety by synchronizing entire methods, making it inherently slow, concurrent hash map offers a more scalable and efficient solution. What is concurrent hash map? Concurrent hash map is a thread-safe implementation of the concurrent map interface, which extends the map interface. It provides concurrency by dividing the map into segments, or buckets in later Java versions, and allowing multiple threads to operate on different segments concurrently. This significantly improves performance compared to hashtable and other synchronized map implementations. Key characteristics. Thread safe. Multiple threads can read and write to the map concurrently without causing data corruption. Scalable. The concurrency is achieved by dividing the map into segments/buckets, allowing multiple threads to work independently on different parts of the map. Non-blocking reads. Reads are generally non-blocking. This means a thread can read data without waiting for a lock, further improving performance. Weekly consistent iterators. Iterators returned by concurrent hash map are weekly consistent. This means they reflect the state of the map at some point in time, but they are not guaranteed to reflect all modifications made to the map after the iterator was created. They are guaranteed to traverse elements only once. Crucially, they do not throw concurrent modification exception even if the map is modified concurrently during iteration. Null keys and values not allowed. Like hash map, concurrent hash map does not allow null keys or null values. Attempting to insert null will throw a null pointer exception. 2. Underlying implementation, Java 8 and later. The internal implementation of concurrent hash map has evolved significantly over Java versions. In Java 8 and later, it uses a combination of hashtable. The core structure is still a hash table, where elements are stored in buckets based on the hash code of their keys. Segments, replaced by buckets/nodes in earlier versions, pre-Java 8. Concurrent hash map used the concept of segments to divide the map into independent parts. Each segment had its own lock. In Java 8, the segments were removed, and the concurrency is managed at the bucket level, also called nodes. Instead of segment locks, fine-grained locking is achieved by synchronizing only the first node of each bucket. Synchronized, or volatile, operations on nodes. The synchronization is handled more efficiently. The first node of each bucket is synchronized during updates. Other nodes in the bucket, within a linked list or tree, might use volatile variables or compare and swap operations for optimistic concurrency. Linked lists or balanced trees. When collisions occur, multiple keys hash to the same bucket. The elements are stored in either a linked list or a balanced tree, typically a red-black tree, depending on the number of collisions. If the number of keys hashing to the same bucket exceeds a threshold, tree_threshold, which is 8, the linked list is converted to a tree to maintain log n, lookup performance. If the number falls below another threshold, untree_threshold, which is 6, the tree is converted back to a linked list. Resizing. When the map becomes too full, as determined by a load factor, it is resized. The resizing process is also performed concurrently. The load factor is typically 0.75. 3. Key methods and operations. Put, K key, V value, inserts a key value pair into the map. It calculates the hash code of the key to determine the bucket, then acquires a lock on the first node of that bucket, if any. If the key already exists, its value is updated. If the bucket is empty, a new node is created. Get, object key, retrieves the value associated with the given key. This is generally a non-blocking operation. It calculates the hash code, finds the appropriate bucket, and then traverses the linked list or tree within that bucket to find the key. Remove, object key, removes the key value pair associated with the given key. It calculates the hash code, acquires a lock on the first node of the bucket, and then removes the element. Contains key, object key, checks if the map contains the specified key. Contains value, object value, checks if the map contains the specified value. This is generally a less efficient operation than contains key because it requires iterating through all the values. Size, returns the number of key value mappings in the map. Because the map is concurrent, the size might not be perfectly accurate at any given moment, but it provides a reasonable estimate. Is empty, returns true if the map contains no key value mappings. Clear, removes all of the mappings from this map. Put if absent, K key, V value, inserts the specified key with the specified value if the specified key is not already associated with a value. Returns the previous value associated with the key, or null if there was no mapping for the key. This is an atomic operation. Replace, K key, V old value, V new value, replaces the value for a key only if it is currently mapped to the specified old value. Returns true if the replacement was successful. This is an atomic operation. Replace, K key, V value, replaces the value for a key only if it is currently mapped to some value. Returns the previous value associated with the key, or null if there was no mapping for the key. This is an atomic operation. Compute, K key, by function, super K, super V, extends V remapping function, attempts to compute a mapping for the specified key and its current mapped value, or null if there is no current mapping. This is an atomic operation. Compute if absent, K key, function, super K, extends V mapping function, if the specified key is not already associated with a value, attempts to compute its value using the given mapping function and enters it into this map unless null. This is an atomic operation. Compute if present, K key, by function, super K, super V, extends V remapping function, if the value for the specified key is present and non-null, attempts to compute a new mapping given the key and its current mapped value. This is an atomic operation. Merge, K key, V value, by function, super V, extends V remapping function, if the specified key is not already associated with a value or is associated with null, associates it with the given non-null value. Otherwise, replaces the associated value with the results of the given remapping function, or removes if the result is null. This is an atomic operation. 4. Code example. V. Advantages of concurrent hash map. High concurrency allows multiple threads to read and write to the map concurrently with minimal contention. Asterisk thread safety asterisk prevents data corruption and race conditions in multi-threaded environments. Asterisk scalability asterisk performance scales well as the number of threads increases. Asterisk non-blocking reads asterisk improves read performance. Asterisk weakly consistent iterators asterisk provides a reasonable view of the map's data without throwing exceptions during concurrent modification. 6. Disadvantages of concurrent hash map. Asterisk slightly higher memory overhead asterisk managing concurrency mechanisms, like locks or atomic variables, requires some additional memory. Asterisk weakly consistent size asterisk the size method may not return the exact, up to the millisecond size of the map due to concurrent modifications. Asterisk null keys and values not allowed asterisk can be a limitation in some cases. Asterisk complexity asterisk the internal implementation is more complex than a simple hash map, which can make debugging more challenging. 7. When to use concurrent hash map. Asterisk multi-threaded applications asterisk when multiple threads need to access and modify a shared map. Asterisk high-performance applications asterisk when concurrency and scalability are critical. Asterisk caching asterisk when a map is used to store cached data that needs to be accessed by multiple threads. Asterisk session management asterisk when managing user sessions in a web application. 8. Common interview questions. Here's a breakdown of interview questions you might face related to concurrent hash map. 1. What is concurrent hash map and why is it used? Asterisk answer, explain that it's a thread-safe implementation of the map interface that allows concurrent access from multiple threads. It's used to avoid data corruption and improve performance in multi-threaded applications where a shared map is accessed and modified frequently. 2. How does concurrent hash map achieve thread safety? Asterisk answer, in Java 8+, concurrent hash map achieves thread safety primarily through fine-grained locking at the bucket/node level. It uses a combination of synchronized blocks, on the first node of each bucket, and compare and swap, operations, on subsequent nodes, to ensure atomic updates. This allows multiple threads to operate on different parts of the map concurrently. 3. Explain the difference between concurrent hash map and hash table. Asterisk answer, the key difference is in their approach to thread safety. Hash table synchronizes entire methods, making it relatively slow. Concurrent hash map provides finer-grained locking, allowing multiple threads to access different parts of the map concurrently, which significantly improves performance. Also, hash table does not allow null keys or values, and neither does concurrent hash map. 4. What are the advantages and disadvantages of using concurrent hash map compared to a synchronized hash map? Asterisk answer. Asterisk advantages asterisk concurrent hash map offers significantly better performance and scalability in multi-threaded scenarios due to its fine-grained locking. Asterisk disadvantages asterisk concurrent hash map has slightly higher memory overhead. The size method might not be perfectly accurate at any given moment. It also has more complex internal logic. 5. What is a weakly consistent iterator, and how does it relate to concurrent hash map? Asterisk answer, a weakly consistent iterator is an iterator that reflects the state of the collection at some point in time, but it might not reflect all modifications made to the collection after the iterator was created. Concurrent hash map iterators are weakly consistent. They guarantee to traverse elements only once and will not throw concurrent modification exception, even if the map is modified concurrently during iteration. 6. Can concurrent hash map store null keys or null values? Asterisk answer, no. Concurrent hash map does not allow null keys or null values. Attempting to insert null will throw a null pointer exception. 7. How does concurrent hash map handle collisions? Asterisk answer, when multiple keys hash to the same bucket, a collision, The elements are stored in a linked list or a balanced tree, red-black tree in Java 8+. If the number of elements in a bucket exceeds a certain threshold, tree_threshold, the linked list is converted into a tree to maintain log n, lookup performance. 8. Explain the use of put if absent, compute if absent, compute if present, replace and merge in concurrent hash map. Answer, describe what each method does, emphasizing that they are atomic operations. Give specific examples, like in the code example above, of how they can be used in a multi-threaded context to update the map safely. 9. How does the size method work in concurrent hash map? Answer, the size method in concurrent hash map returns an estimate of the number of key value mappings in the map. Because the map is being modified concurrently, the size might not be perfectly accurate at any given moment. 10. How is resizing handled in concurrent hash map? Answer, resizing is performed concurrently. When the map becomes too full, determined by the load factor, a new array is created, and the elements are transferred from the old array to the new array in a concurrent manner. This allows other threads to continue accessing the map while the resizing is in progress. 9. Tips for the interview. Understand the trade-offs. Be aware of the advantages and disadvantages of concurrent hash map compared to other map implementations. Know the Java version. Be aware that the implementation details of concurrent hash map changed significantly in Java 8. Mentioning this shows that you are up to date with the latest developments. Focus on practical usage. Be prepared to discuss real-world scenarios where concurrent hash map is a good choice. Code examples. Having a few simple code examples ready to illustrate how to use concurrent hash map can be very helpful. Practice. Rehearse your answers to common interview questions. By mastering these concepts, you'll be well prepared to tackle concurrent hash map questions in your Infosys interview and demonstrate a solid understanding of concurrent programming in Java. Good luck.